In this video, we're going to look at an important type of functor called a representable functor. So a representable functor, first of all, is a set-valued functor. So we can see here we have a functor R going from the category C to the category of sets. And we have it stated as contravariant, but there's a covariant formulation as well for this definition, which we can look at as well. So a contravariant set-valued functor R going from the category C to the category of sets is called representable by an object C in C if there is some natural isomorphism, lambda, going from the contravariant home functor, which has target object C, this fixed object C here, to the category of interest R here. And if you can find that natural isomorphism, then you can call your functor R representable. And so what is a natural isomorphism again? Well, a natural isomorphism is a natural transformation. So we can see lambda here is a set of components for each of the objects of C, X. And so this natural transformation has to have every component be an isomorphism. So if you have a natural transformation where all of the components are isomorphisms, then you call that a natural isomorphism. And since these are set-valued functors, we know that if there's an isomorphism between them, that means that there's a bijection between them because all of these components are isomorphisms in the category of sets. That is, they are all bijections. To get the definition for a covariant representable functor, it's pretty easy. You just take the exact same definition stated in the exact same way, except for here you replace the contravariant home functor with the covariant home functor. So recall that the equivalent of this contravariant home functor with target object C for the covariant version would be home C blank, which is the covariant home functor with source object C. So why are representable functors interesting? Well, they're interesting for the reason that they get their name, which is that they're representable by some object. So this fixed object C in the category C, this domain category here, is sort of a representative for this entire functor R. What does it mean to say it's a representative? Well, in this case, the natural isomorphism guarantees that the patterns of R, the patterns of the transformations of the functor R, are identical to the patterns of the transformations of the contravariant home functor home blank C. So what that means is that R may be some very complex or very obscure transformation that maybe we don't understand a lot about, but if we can somehow reduce it to saying that we know that it's representable, then we're basically saying that it's naturally isomorphic to this contravariant home functor. And the contravariant home functor simply represents how all of the objects of the category interact with one single object, this fixed object C. So you're basically saying I can reduce all of the transformations of R down to simply the interactions of the category with a single object in that category. And so oftentimes that's going to make it much simpler to understand. So one question we might ask ourselves with that definition in mind is, when do we know that a functor is representable? So we're saying that it can be helpful to figure out that some functor R is representable, but how can we do that? What's a way to know that a functor is representable? So that's what our first result is going to be. So we'll look at one situation where we know that a functor is representable. Suppose we have some covariant functor f going from a category D to a category C, and that C is some object in C. We're going to define the expression home f blank C to be simply the composition of the contravariant home functor home blank C and our functor f. When that's the case, then we can say the following. home f blank c is representable if and only if there's a couniversal for CF. So basically we can see that there's a very tight relationship between representability of this composition functor here and the couniversality concept that we covered in detail in a previous video. In order to prove this, let's unpack these definitions a little bit more. So we just defined representability. So for home f blank c to be representable means that we must have some natural isomorphism lambda consisting of all the components of lambda x, and that goes from the contravariant home functor, home blank d, into our functor of interest, home f blank c, for some d in d. So there's an object d in d such that this natural isomorphism holds when it is the target object of this contravariant home functor. So if we draw that out one more time, let's suppose in our category D over here, we have some morphism f going from x to y. Well, then on the top here, our first functor is home blank d, and that's a contravariant functor, so it's going to go from our image of f is going to go from home y d into home xd, and on the bottom we're going to have our functor of interest, home f blank c, and so of course that also needs to be contravariant, and that also explains why f needs to be contravariant, because we need the composition of these two to be contravariant. So if f was also contravariant, then it would go contravariant, which would basically flip it and then flip it back, which would make it a covariant functor. The composition would end up as a covariant functor, but we need this composition if we want it to be naturally isomorphic to a contravariant functor. We need it to be contravariant. So the same will happen on this side. We'll get home y f y c and home f x c. And what is the image of f under home blank d? Well, that's just the contravariant home functor, so that's going to be preceded by f. And then what is going to be the image of f under home f blank c? That's a good exercise, so maybe pause the video here and think, what do we fill in the blank up here? And so first we're going to apply f, and then we're going to apply home blank c. So to get f, we'll get f of f, and then we'll get preceded by f of f. So this is what we'll end up with on the bottom. And then we say that now we have this natural isomorphism. So for each component, there is, in this case, lambda y, in this case, lambda x. And not only that, but each one of these components is actually an isomorphism. And we're in the category of sets on this side. So when we say that these are isomorphisms, we say that they are bijections, set bijections. Now for this side, if we say that there's a couniversal for CF, that means that there has to exist some pair DU where U goes from f of D into C, where D is in D, such that for any x in D, and for any f going from f of x into c, there exists a unique tau of f going from x into d such that f is equal to u after f tau f. So again, this does look kind of terse and complicated, but if we just remind ourselves of the diagram, it becomes pretty clear again. So if we have on the left our category D, and we have our co-universal object D in D, and we have our functor F, then we have on this side our co-universal morphism U going from f of D into C. And the statement here says that for any x in D, and for any morphism f going from f of x over here into C, there exists a unique tau of f going from x into D such that this diagram commutes. This is f tau of f. This is tau of f. So that's the diagram for this definition. So we're saying that these two properties are equivalent. So it could be helpful for the rest of the video to draw this diagram out for yourself and refer to it when you need to in terms of proving some of the results that we're going to see. So let's prove this statement now, starting in this direction. So we want to assume that home f blank c is representable, and then prove that there exists a co-universal for CF. So we just saw that if home f blank c is representable, then we have some natural isomorphism lambda going from the contravariant home functor home blank d into our functor home f blank c for some d in D. But if you recall the video on Yoneda's lemma, you'll remember that anytime we have a natural transformation where the domain is a contravariant home functor, we actually know exactly what that natural transformation is going to look like. It can only take on a certain form. And so if you don't remember that, you can go back and check out the video on Yoneda's lemma. But recall then that lambda x applied to some d going from x into D is going to be our functor home f blank c applied to D, followed by lambda d 1d. So these natural transformations depend only on the value that the d component of lambda assigns to the identity on D. While we saw that this functor applied to D is going to be f of D precede by, and that's going to be applied then to lambda d 1d, which is going to be equal to lambda d 1d after f of d. Well, notice here that if lambda d 1d were to take the place of u in our co-universal equation, this would look a lot like the right-hand side of our co-universal equation. So let's try taking the pair d lambda d 1d which goes from f of d into c. It follows the component d in the natural transformation. And let's see if we can show that this is actually a couniversal for CF. So we need to take some x in D and some morphism f going from f of x into C. Then we know that lambda x is bijective because it's a natural isomorphism. It's a component in this natural isomorphism, and that natural isomorphism is in the category of sets, which means it must be a bijection. So lambda x is bijective, and so that means there's only one d going from x to d in D, such that lambda x of D is equal to f, right? It's bijective, so whatever f this is, there's only one d that's going to map to it, since the mapping is 1 to 1. But then we get f equals lambda x of d, which is equal to lambda d 1d after f of d. But then we have that d satisfies the commutativity property that we needed. This is our u, lambda d 1d, and f of d. So obviously d satisfies the property that we needed for the couniversal. There's only a single d that does it as well. So that means that d lambda d 1d is couniversal for CF. We have a unique morphism that satisfies this commutativity property. So that proves this direction. Now we just need to prove this direction, which is we need to assume that there is a couniversal for CF, and we need to prove that in that case, home f blank c is a representable functor. So if there is a couniversal for CF, that means there exists some pair D, U, which is a morphism going from f of D into C, such that for all x in D and for all f going from f of x into C, we have a unique tau of f going from x into D, such that f equals u after f tau f. So this is just the definition of couniversality unpacked. But notice something in this definition, which is that each tau of f is unique. Every f of x can only map to a unique tau of f. And so we can actually define a properly defined function, which is, call it lambda x, going from home fx, c, into home xd, which is defined by simply alpha x of some morphism f going from f of x into c. So the domain is morphisms from f of x into c. So if f is some morphism from f of x into c, then I just map it to that tau of f. And since it's unique, this is a properly well-defined function. Notice two things about this function. The first is that it's injective, and we can see that by setting alpha x of some f1 equal to alpha x of some f2, where those are both in this home set here. And if that's the case, then tau f1 is going to be equal to tau f2. But if that's the case, then we can apply the same thing to both sides to get u after f tau f1 equal to u after f tau f2. And if that's the case, then we know that by the couniversal property, we have this equation here. So we have that u after f tau f1 is equal to u after f tau f2, and this side is equal to f1, and this side is equal to f2, but we get that f1 is equal to f2. So this mapping is in fact injective. The second thing about this function is that it's also surjective. And we can see that by taking any element in this home set here, the codomain, and making sure that there's some element in this home set that maps to it by alpha x. So take some d from x to d, while then using the right-hand side of our equation here, u after fd, what's that going to go from? F of x into c. But if that's the case, then it's in this home set, which is the domain of alpha x. So we can apply alpha x to u after fd. And what do we get if that's the case? Pause the video here if you want and figure out what the right-hand side is. Well, it's just going to be d, because effectively we need some morphism that satisfies u after fd here is equal to u after f tau of f. Well, it's pretty obvious which tau of f is going to satisfy this. It's d, because it's already in this format. Both sides of this equation are already in the same format. So obviously if I plug d in here, this equation is going to work. And so the last thing we just need to check is that that d is unique, but it is, because u after f of d goes from f of x into c, which is what we need to satisfy this co-universal property up here. And so we know that there's only a single d that satisfies this equation, and since this d obviously does, it's the only one that can. So it is unique and it satisfies the definition, which means that lambda x of u after f of d is equal to d, which means we have some element of home fxc which maps to d. And so this function is surjective. And so what we can say is that it's surjective and injective, and therefore it is bijective. But notice again that this argument applied to any x in D. So that means we can create an alpha x for any of the x's in D, and this argument will apply equally to all of them, which means that actually the set of all alpha x for all x in D is a family of bijections So since we have a family of bijections where there's one for each object in D, which you could maybe think of as the components, we can try to define a natural isomorphism going from home F blank C into home blank D. And we can ask ourselves, is this a natural isomorphism or not? And the question then becomes, does it satisfy the naturality condition? Because we already know that they're bijections going from home sets home F X C to home X D. but we need to ask ourselves, does it satisfy the naturality condition in order to be a natural isomorphism? And so what is the naturality condition in this case? Well, it's the opposite of what we drew in the diagram at the start of the video, in the sense that we had a natural isomorphism going in this direction, and so the commutativity property was the other way. But in this case, since we're starting at home f blank c and going into home blank d, the naturality condition is going to be lambda x after precede by f of f equals precede by f after alpha y, and that's for all f going from x to y in D. So if we can prove that this commutativity property holds, then we can say that these are in fact components of a natural isomorphism. In order to see that this is true, let's take some g going from f of y into c. Then we can apply the left side of this equation to that g. And so if we have lambda x after precede by f of f applied to g, that's going to be lambda x applied to the result of precede by here, which is going to be g after f of f. And this is going to be equal to, well, let's notice something. G goes from f of y into c, which means we can map it by alpha y. So we would have some tau of g that satisfies the couniversality property. And that one would have to go from y into d in order for it to be able to satisfy our equation. And if that's the case, then we can compose with f on the right, because f has the codomain y. So we'd have that tau of g after f would be going from x into d, x into y, y into d. And if that's the case, well, these are bijective, and this goes from x to d, which is in one of these home sets, home xd. And so if that's the case, then we have to have some element of home fxc that maps to it, because these are all bijections. So if that's the case, then we have to have some c. There exists a unique c going from f of x to c in c, in the category c, such that alpha x maps c into our value here, tau g after f. And if that's the case, then we can plug this into our couniversality equation to get that c must be equal to u after f of this value, tau of g after f. And so we could break this functor up here to get u after f tau g after f of f. But this part is just g, right? This is the right-hand side of the couniversality diagram for g. So we would just call this g after f of f, which is exactly the expression that we have here. So this is actually equal to alpha x of c, right? C is equal to g after f of f. G after f of f is equal to c. What's alpha x of c? Well, we just defined that. It's tau of g after f. That was exactly how we defined c, was the value that mapped to that. And what's tau of g? Well, obviously, it's alpha y of g, right? That's exactly how tau of g is defined, is what alpha y of g will map to after f. And composing with f on the right-hand side is just applying precede by f. So this is precede by f after alpha y of g. But notice that's exactly what we needed to prove. That's the commutativity property in this naturality equation. So the naturality property is satisfied, and this question mark can turn into a check mark because we do in fact have a natural isomorphism. We have a family of functions. Each one is a bijection in the category of sets, going from this functor to this functor. And not only that, but they all satisfy this naturality property, meaning that it's a natural isomorphism. So the question is, have we proved that home f blank c is representable? In a certain sense, we have, but there is one more step. What is the last step? Well, to be representable, you need to have a natural isomorphism going this way, from home blank D into home F blank C. But as you might have guessed, if we have a natural isomorphism going this way, then we also have a natural isomorphism going back the other way, which is this direction. And so we are in fact representable. And if you don't believe me, that's a good exercise. Prove to yourself why. If there's a natural isomorphism going in one direction from one functor to another, then there must also be a natural isomorphism going from the second functor back to the first. So you can always flip back and forth, just like a bijection for a function, basically. It's the same kind of idea. So that is both directions. We've proved that if home f blank c is representable, then there's a couniversal for cf. And if there's a couniversal for cf, then home f blank c is representable. And we'll call that QED for this result. The other result we're going to prove about representable functors is, suppose I have two representable functors f and g, both going from a category C into the category of sets, and suppose that the natural isomorphisms that make those functors representable are alpha and beta. So there's some object A in C such that alpha is a natural isomorphism going from home blank A into F, and there's some object B in C such that beta is the natural isomorphism going from home blank B into G. Then, for any lambda, which is a natural transformation from F to G, we can actually replace the composition of alpha and lambda. So alpha goes from home blank A into F, lambda goes from F into G. So this composition is going to go from home blank A into G. We can replace that by simply the other natural isomorphism composed with follow by H for some unique H from A to B in the category C. And that may be helpful for us because in general, follow by H is quite a straightforward natural transformation. We understand a lot about it and how it works. So maybe studying this natural transformation will be a lot simpler than studying this natural transformation. And since we know that they're the same, we can just study the simpler version instead. So in order to prove this, we need to take some natural transformation lambda going from F into G, and then we need to find our unique H that makes this possible. So the composition of any natural transformations is a natural transformation. And since we have a natural transformation going from home blank A into F and from F into G, and then we also have a natural transformation going from G into home blank B, what is it? Well, it's beta inverse X. You just take the inverse of the isomorphism for any component, and all of those will form a natural isomorphism for going in this direction. So basically what we can say is we know that there has to be a natural transformation that is the inverse of beta after lambda after alpha. So if we compose those, then we get another natural transformation, and this has to go from home blank A, here, the domain of alpha, into home blank B, which is the codomain of the inverse. It's the domain of this one, so it's the codomain of the inverse. And if that's the case, then we know exactly what it looks like, right? Because we've studied what it looks like to take a natural transformation between two contravariant home functors of the same category. And so it's going to be equal to followed by h for every component x in C for some morphism h going from A to B. So we know that if we have a contravariant home functor, home blank A, and a natural transformation going into another contravariant home functor, home blank B, then those natural transformations always take the form followed by h for some h going from this target object to this target object. So what we get is that if x is in C and f goes from x to A in C, then we have to have the inverse of beta x after lambda x after alpha x applied to f has to be equal to followed by h of f. But if that's the case, then we can apply beta to both sides of this equation to get lambda x after alpha x of f is equal to, well, those betas are going to cancel, and so this side we're going to have beta x after followed by h applied to f. But what that proves is that this natural transformation composition is equal to this natural transformation composition, because this is for any f. So what that means is that we have lambda after alpha is equal to beta after followed by h as natural transformations. And that's what we needed to prove. So we have such an h, and all we need to do now is confirm that it's unique. So to do that, let's suppose that there were some other morphism h2 going from A to B also, that also satisfied this natural transformation equation. That is that lambda after alpha is the same as beta after followed by h2 this time. And we need to show that actually h2 has to be equal to h, this h here, guaranteeing that it's unique. So in order to do that, we know that if this is the case, then for any f going from x into A, we have to have lambda x, just applying this, after alpha x of f is going to be equal to beta x after followed by h2 of f. But remember that this equation still applies for h too, so not h2 but h as well, this h here. So let's add that one to this side instead. So we know that this side is equal to beta x after h followed by applied to f is the same as beta x after followed by h2 applied to f. But now we can cancel these two sides because beta x is invertible, they're isomorphisms, so we can cancel that side. And if that's the case, then we have h followed by is equal to h2 followed by for any f, so that is the natural transformations followed by h and followed by h2 are actually equal. But if that's the case, we need to have that h is equal to h2. And so this step here is actually a pretty good exercise. How do we know that just because the natural transformations followed by h and followed by h2 are equal, that h and h2 themselves as morphisms have to be equal? So you can try that as an exercise. But in any case, this proves that we have such an h and that it's unique, because if we had another one, it would have to be equal to the first one. So that's QED for the second result. So let's just summarize everything we've said. The first is defining what a representable functor is. So a functor f going from C into set is representable by some object C in C if there's some natural isomorphism lambda going from the home blank C functor, the contravariant home functor with target object C, to our functor f. And if that's the case, then we saw two results that we proved. The first is that if there's some covariant functor, f going from D into C, then for some object C in C, home f blank C is representable if and only if there is a couniversal for CF. So we defined what this was. We reminded ourselves the definitions of couniversal and representable, and we proved that this was an if and only if condition. And finally, we proved that if f and g are both representable functors, both going from C into set, and f has the natural isomorphism alpha associated with it, and g has the natural transformation beta associated with it, then for any natural transformation lambda from f to g, we have a unique h going from A to B in the category C, such that we can replace the composition of this natural isomorphism with the natural transformation by simply this natural isomorphism and follow by h for that unique h in C. So that's everything we have to say about representable functors in this video. But of course, there's lots more, so you can look into some other results and try to prove some other results if you're curious.